So let's start. So first of all, before we begin, I'll not keep you. I know it's Labor Day weekend is coming up, so I'll not keep you guys very long. This is a smaller lecture focused on exploratory data analysis, and I will be giving you guys some examples on how exploratory data analysis works, what we do about it, and I'll give you some examples from my current work, and hopefully it'll be useful for you. Some news, you already know that your task 1 data set will be given to you next week, early next week. So you can start working on it. It's not very difficult. The data sets are the data set that will be given is fairly simple, and you can and the tasks that you have to do are not very difficult. It shouldn't take you very long. Keep aside a couple of hours, and you should be able to do it. So yeah, I'm getting to you on the volunteer stuff. So this is something Dr. Eick wanted me to let you guys know. So Amanda Foster, she's a former student of Dr. Eick's. She's a solution analyst for Phillips 66, and she wants about 10 students to attend a volunteer event at Houston Food Bank, as you can see here. UHCS and other departments at UH have been working with Houston Food Bank for a while now, so it's a good choice. And you can work at Phillips 66 for they have recruiters and stuff coming on over there. So the date is okay. The date's not here, but the date is actually Friday, September 9th. So note that down. And if you want to volunteer, just send either one of the TAs, me or Dr. Eick, an email as soon as you can, and we will forward it to Amanda. So it's at 535 Portwell Street, which is somewhere northeast of Houston. It's like 15 minutes from campus, so it should be. You should be able to make it. It's on Friday, next Friday, Friday the 9th. So yeah, send either me or your other TAs or Dr. Eick an email, and we should be able to handle that for you. So yeah, it's a good opportunity. So try and join in. So let us begin with exploratory data analysis. So first of all, if you have the TAN book on exploratory, on the TAN Steinbeck Kumar book that has been recommended, you are going to need like the first edition to find exploratory data analysis, because they removed that section and they merged it with like other data mining stuff. So if you have that book, take a look there. So today we'll be talking about, like I said, like why do we need to explore before doing data analysis, and like what are the kinds of statistics that we will be using for data analysis. So basically, exploratory data analysis means getting to know the data, right? So before you begin like diving into the depths of the data itself, you need to figure out like what's going on in the data, like what is it trying to say. Before you do this, before you have a hypothesis, like before you decide what exactly you're going to do with the data, like before you have like, okay, the data that you have is going to tell you this thing. Before you know that, you need to explore the data to find out like what kind of patterns are in the data, what kind of background information is in the data already, and things like that. So like I said, you'd want to do exploratory data analysis because you want to understand what the data is trying to tell you before you dive deep into the data to figure out what exactly is in it. So you need to do this before you start like actually pre-processing the data and dropping dimensions and dropping tables and modifying the data, extracting any kind of information from the data. You need to figure out what's in there. So create a map of the data. A major, like this is usually turns out for a data scientist, this is actually a very interesting part of like your work. So what happens is, first you end up doing like your boss or whoever, she comes in and gives you like a blob of data, right? A large CSV file, a large geospatial file, something that like you don't really know what's going on in there. And you have a vague idea of what you need to extract from the data. But before you dive into, like before you start analyzing the statistics and everything, you need to figure out what's going on over the data. You need to find out, like, are there any patterns that strike out at you? Is there anything going on that's like very unusual? Are there any outliers? Is there any part of the data that makes no sense at all? Are there things that you need to drop from the data completely? You need to figure these things out before you spend your time like actually working on the data. So let me give you a couple of examples quick. So this is an artificial data set, right? So you can see that uh, this this is essentially like a fish, but you see how the data is structured. Like you can see there are clear patterns in this. There's this eye shape with like two irises. There's this reverse question mark. There's this, I don't know, S symbol. There's this equal symbol. But these are all very distinctly positioned, and all the little black dots on the outside, they don't fit into any particular pattern at all. So you see you can very easily, without like doing any kind of mathematical analysis or statistical analysis, just with your eyes, you can see that there are about 1, 2, 3, 4, 5, 6, 7, 8, 9, perhaps 9 clusters, perhaps 7 clusters, depending on if you want to classify like each of these separately or individually. So just by looking at the plotting of the data, you can find out like, okay, what's going on in the data, like what kind of analysis you might need to do later on. And so these things just pop out at you. Another very like minor thing that you see here is because you plot the data without like having any preconceived notions of like what is in the data already, right? If you don't do that, what happens is you sometimes miss like the forest for the trees. So I don't know if you guys have heard of it. There's a very famous video of like a bunch of people playing like basketball, and then a person wearing a gorilla suit just like moonwalks through that entire video. And someone tells you, okay, count how many times the basketball has been passed in that video, passed between the people in the video. And if you focus on just counting the number of times the ball is being passed, you miss the gorilla, the man in the gorilla suit moonwalking through the video. So that's like a very famous example of like situational awareness. But that is something that also happens in data analysis. So a very famous example of this is actually this. I hope you guys can see this. So this is a paper that came out a couple of years ago, where they created two groups, a control group of people who were not told what they were looking for in the data, and a group of people who were told that you need to figure out some correlations between number of steps taken by a person running on a treadmill or something, and their BMI. So the people who were not told to what they were looking for in the data, they plotted the data and found out that the data is essentially nonsense, because the data is plotted in the shape of a gorilla. And the people who were told what they were looking for essentially missed the gorilla in the data. So as you can see here, like the people who were focused on whatever hypothesis they were trying to figure out from the data itself, they were far more likely to not see that the data actually didn't make any sense, that there's a gorilla hiding in the data. So you need to be careful about things like this, right? So whenever you're given like a big blob of data, try and just plot it out, look at like some of the summary statistics, but don't rely over much on like statistics like mean, mode, median, all of that. that too can be faked, or that too can give you like misleading signals of the data. Like very different distributions of data can have the same mean, mode, median, and other summary statistics. Uh, so yeah, this is what we'll be talking about today. Like, what are the statistics and what you need to do about it. Uh, so where does exploratory data analysis fall in the data analytics platform? So first you get the data, then you do this kind of exploratory data analysis where you try to figure out what's going on in the data. Then once you have seen that, then you start cleaning the data and pre-processing the data. And then finally, you start to extract what knowledge can be extracted from the data. Um, so one of the things is because you generally don't do data cleaning or data pre-processing before like doing some sort of exploratory data analysis. The reason for that is sometimes like the data is just wrong. Like humans, a lot of the time, a lot of the data that you'll be doing is not just collected by machines, but is actually inputted by humans. And humans tend to make like mistakes. And so let me give you another new example of what happens when you get human related like data from humans and then you start like working on it without like actually exploring it. So there was an election yesterday or a couple of days back in Alaska. And so here's an interesting bit of data that came out of it from the Alaskan Data Commission. This is the breakdown of Alaskan voters by gender. So you can see that like the majority of the data is male, female, and I don't know what U stands for here, probably unknown. But you can see like a bunch of the data makes no sense. So this kind of like your gender is probably not Italy or Australia or Canada or the US or null maybe. So this kind of outlier detection, if you don't do your first form of exploratory data analysis and figure out what the outliers are and what kind of data doesn't make sense, you're going to get in trouble when you start like working on the data and then you figure out a bunch of your your analysis pipelines are breaking because someone put in null in gender and your I don't know your natural language platform does not know how to deal with that and everything breaks. So yeah. Uh, and like if you think that this is like uncommon, but it's not. Like this is very common, especially wherever you have like a volunteer collected data or crowdsourced data of any kind you're working on. You have no idea what people are going to put enter into any of the fields. They put in like absolute gibberish sometimes. So you, as data scientists, you're going to have to deal with that, and you deal with it during the exploratory data analysis phase. So historically, like a bunch of the exploratory data analysis was focused on visualization. So you plot like bar charts or Sankey diagrams or any other kind of visualization fields that tells you like how the data is distributed. Then you try to figure out, okay, what kind of, how, maybe not the exact outlines of what clusters are in the data set, but like just random things of like, okay, there are maybe two clusters. Maybe the data set is distributed bimodally or unimodally, or like there are multiple modalities in the data set. Maybe a bunch of the data can be just discarded because they are very clearly anomalies, like in the Alaskan gender thing, where you can very easily discard a bunch of the data. But then again, you need to figure out, do you discard also unknowns? Do you discard nulls? And then you need to figure out why did that happen? If there is an error in any one of these fields, there may be errors in other dimensions as well. So you need to figure out the source of the error so that the error does not like propagate through your entire analysis pipeline. So formally in data mining, when you try to extract knowledge from the data, people generally don't really talk about clustering and anomaly detection, error detection. or it's also sometimes called noise detection, noise minimization. There are many kinds of like many terms for this, but yeah, they're not really parts of data mining as such, but they are part of your analytics platform. So today we probably won't get into much depth into visualization, but we will talk about summary statistics a lot. So yeah. So if you have any questions, uh, yeah, yeah. So I see your jokes here, but yeah, if you have any questions, just let me know. Otherwise, we are going to move on. So a very popular data set for data science purposes is the iris data set, where you classify 3 different flower types: the setosa, the virginica, the versicolor, and like you classify them by sepal width, petal width, length. Uh, so this is a very, very common and very, very popular data set that you will be seeing in if you are doing any kind of data science related work, whether it's in computer science, whether it's in statistics analysis in math, or anything like that. Before we go into like much detail into this, let me show you like what kind of data that. Oh yeah, let me just clarify. It is a like the Philips 66 thing. It is an industry opportunity. There is it's a recruitment opportunity. You're going there to be nice to show that UH is interested in the Houston data bank thing, but you're also going there to be recruited by Philips 66. So yeah. Um, what was I talking about? Okay, yeah. So data sets. Like the iris sample data set is a very clean, very nice data set, but I want to show you like what real world in the real world what the data set would look like. So let me show you something. Yeah, okay. So this is a data set that I work with. It's from a company called SafeGraph. And what they do is they collect in your cell phones, a bunch of your apps, when you first open your apps, they say like, okay, we'll be collecting some data from you uh, as you're using this app. So SafeGraph is one of those companies that buys the kind of random aggregate data that various random apps collect from your cell phone. And what they do using that data is essentially track people. So they anonymize the data, and then they're able to tell you like, okay, like 500,000 people live in, say, I don't know, within the loop in Houston. Okay, then what percentage of people are moving between like different areas within Houston at different time periods? So during office hours, how many people are moving from a residential area to, I don't know, to downtown? Like how many people are moving from Sugarland to, I don't know, like to downtown or to Midtown? During Saturday, during Friday evenings, during weekend evenings, how many people are going to, like, I don't know, the wherever Houston's party places? I wouldn't know. So that kind of summary statistics based on devices is a lot of data. Like I say here, like gigabytes and gigabytes and terabytes of data. So what we do is we use this data, this aggregated anonymized data, and then we explore the data and we figure out like, okay, what kind of statistics are we seeing here? Like when are people are moving about, when on aggregate, when are the strip malls the busiest on aggregate, when are like I don't know, the pharmacy is the busiest. When are people going to car shops? When are people going to bookshops? So on aggregate statistics like this, you can't just like, I don't know, plot that data directly and see what's going on. You take like samples of the data at different points, and then you try to plot it, and then you see what's going on. The reason why I use this kind of data is because we use it for agent-based modeling. So we use the data that I just showed you, like that safe graph data, and we use it for things like this. This is a model that this is focused on like a very little known American city called New York. And this is focused on the Bronx. So we take the data that you saw, like the safe graph data, and then we use that to figure out like, OK, how many people are in general moving about the city. And then we use that information, that statistic, to create epidemiological models. Essentially, we try to figure out like, OK, if there's some sort of infectious disease like spreading in the city in like say 2020, how would that disease spread about? So how are infected people moving about? Like what are infected people moving to like the offices? Are infected people going to, I don't know, malls for shopping? So if they are, then how would the disease spread? And we use the safegraph data for this purpose. And if we don't know what the data looks like, we wouldn't be able to like go this in depth into this kind of data directly. So as you can see, if you zoom into the data, like these little green dots and red dots, and like these are all infected people and stuff like that. So they are placed based on the safegraph data. And that safegraph data essentially tells you like where the biggest concentrations of people are and where would they be moving as you are simulating the city. And then you can find out different kinds of statistics to figure out, OK, if that information is accurate or not. I'll give you another example of the kind of data that we work on, which is once again very different from like the standard iris sample data that you see here, which is just basically a CSV file with numbers and commas. But data does not, like real world data does not always look like that. So you need to be prepared for like extremely complicated kinds of data sets. So what are some summary statistics, right? So summary statistics are like a quick way of summarizing the data. They are not always accurate, so you shouldn't like rely on them too much, but they are useful. So the most common summary statistics that all of you have heard of and probably used in your lives is the average or the mean and the standard deviation. A big advantage of summary statistics is that given that your data set might in the real world, your data set might be huge, hundreds of thousands to billions of rows, you need to like your statistics, like whatever your quick pass statistics are, they need to be very fast. So one of the advantages of this is like mean, standard deviation, etc. They're very quick. They're essentially linear time. So they go through the data you go through the entire data set once and you're able to do it. And modern computers are good enough to that, like unless your data set goes up into like the billions, finding summary statistics is a very quick, it's a very quick process compared to like you want to do like Kolmogorov-Smirnov test on your data set. That's going to take you a couple of hours if you do it on a 10 million row data set. If you just want to calculate like mean, standard deviation and things like that, they're pretty quick. So the other thing is like you want to figure out like the very common set of statistics like frequencies, modes, etc. Like that tells you like finding out like the frequency or the mode, which is like the highest, most frequent attribute, would tell you. Oh wait, hang on. Yeah, sorry. So where was I? Given like the whatever data set, like whatever value is like the highest frequency, it essentially tells you whether the data set that you have collected is a representative sample of whatever you're trying to wherever the data is coming from. It also tells you whether the data set is bimodal or unimodal, or whether you can partition the data set into like to save you more time in like analysis. It also tells you uh, whether there are outliers, because if there are data points that are very far from the like the central frequency or the mode of the data set, but it is like it is a smaller peak compared to like the actual peak of the data, and you know that there might be something wrong with the data, or there might be like very widely scattered peaks in the data, and you might need to deal with that. Um, Once again, you all know like the different types of data sets, like categorical, etc. So frequency and mode are very commonly used with categorical data, because if you have continuous data, frequency and mode does not really make sense. So what makes more sense is percentiles. If you have given like, I suppose most of you have sat for like competitive exams. So if you're sitting for a comp exam, a percentile is a far more useful notion, you know, because a percentile tells you like, okay, what percentage of the entire population falls under a particular percent. So if you are within the 99th percentile, then you know that what, like if your score, for example, is within the 99th percentile, then you know that 99% of the people who have sat for whatever exam or quiz have scored lower than you. Like which is useful for figuring out, once again, for figuring out outliers, for figuring out top performers or things like that. A bad example of this is uh, a lot of companies used to, I don't know if they still do, they used to every year upon year, they used to shave off the bottom 10 percentile of their workforce. I think General Electric was very famous for doing this, where they would like where they would every year just remove the bottom 10 percentile of their bottom 10 percentile of their performers every year, so that like the new hires could always just kept on making the company better, so to speak. Whether it's successful or not, I'll leave you to think about GE. Um, so another very useful like plotting mechanism are box plots, because box plots are a very easy way of looking at like large data sets, like a single dimension of a large data set, and then you get a very good idea of what that data set is. A box plot, if you haven't seen it before, is essentially a box showing the middle 50 percentile of the data, where where the largest concentration of the data is, and then it tells you like what the average distribution of the data spreads out to, and then it also gives you some idea of like which data sets might or might not be outliers. Once again, don't rely completely on box plots or any kind of summary statistics to figure out outliers, because the data may lie in many cases. So uh, now we saw summary statistics as mean and standard deviation. Now standard deviation is a measure of central tendency, and mean and median are measures of location. So the mean and median would essentially tell you what values the data set is centered around. It is whether you're doing clustering or classification or any kind of tasks where you need to figure out how the interior of your data is structured with respect to other parts of your data. You need means and medians. The problem with mean is, as it's said here, is that it is very sensitive to outliers. There's a very common joke that on average, a human being eats 3 spiders a day or something like that, like 2 spiders a day or whatever. And well, you might be thinking, okay, people don't, that doesn't really make sense. Why would people be eating 3 spiders a day? But turns out some weird person living in a jungle somewhere eats 20,000 spiders a day, and that tends to skew the average. Um, so yeah, that's a pretty silly joke, but it tells you like what I'm talking about. Like massive outliers will pull your mean towards the outliers, right? And you need to, so you can't always rely on means. And in those cases, the median helps. The median would essentially tell you this, no matter what the outlier, what the outliers are, it will tell you where the center of the data is. It you in most cases, unless if you don't have like major outliers, mean and median fall like very close to each other, fall within like 2 or 3 sigma of each other. But like in real world data, you will have like outliers, and they're going to skew your mean. So you're going to have to be very careful about that. So the other measures of spread, like I said, uh, as opposed to measures of location and central tendency, are range and variance. Range is a very simple concept, right? You from the name itself, you understand that range means how your data is stretched, like what is the difference between maximum and minimum. The variance or standard deviation tells you, okay, how given that the center of your wherever the center of your data is given a normal distribution of data, uh, how much on average is like on average, how far away is your data, are your data points from that central point. So if you have like a large standard deviation, then you can guess that your data is flat, essentially. Like like at any point you can't really tell, like given a random data point, if you sample one of the data from your data set, you won't be able to tell whether that data set is like the most among the most common or not. But if your standard deviation is very small, then you know that a large percentage of your data falls within like a peak, essentially. So standard deviation is very helpful for telling you, like, okay, if you randomly sample from your data set, then whether you are getting an outlier or whether you're getting something very representative of the sample, right? But once again, like outliers are going to like wreck your analysis platform. So you need to figure out like things like mean absolute deviation, absolute average deviation, median absolute deviation. Um, you can see the formulas for them here, but what you essentially end up doing is finding the mean of the data set and then figuring out how far you are from that mean and then averaging it out, essentially. You can see the formulas for AD, MAD, and interquartile range. So interquartile range is actually far more useful as a visualization or like as a quick understanding purpose rather than like any kind of like actual statistical purpose. Interquartile range basically tells you, similar to standard deviation, it tells you where the middle 50% of your data lies. So if you where the range between 75th percentile and 25th percentile of your data. So this is a very common rule of standard deviation, where around 67% of like 68.27% of your data is going to fall within like one standard deviation of your central tendency. Now, to be very clear, this is assuming a normal distribution or a Gaussian distribution. If your distribution has multiple peaks or if it is skewed in any way, then this does not work at all. Like, be very careful because not in the real world, If you collect data on first glance, they might like if you sample it correctly, they might they might be Gaussian, they might be distributed normally. But if the process that you're if your data that you're sampling is not normal, then your standard deviation rules where you know that 67% of your data is going to fall within one standard deviation, then 95 is going to fall under 2, and 99.7% is going to fall under 3 standard deviation. That while that might not always be true. So be very careful for applying any kind of statistical pre-knowledge on non-Gaussian or non-normal distribution. Because that has tripped me up, and that will probably trip you up as well, fairly often. So yeah, like I said, what you understand from figuring out whether something falls within one standard deviation or not is it essentially tells you that how many times something is going to be within that range, right? So whether it's but if something is within one standard deviation, then outside of that range, then if something is within one standard deviation, if it means 67%, so it roughly means 2 out of 3 times you sample something is going to fall within that range. Or in the other ways, like 1 out of 3 times you sample something is going to fall out of that range. So that way, if you say something like it falls within 3 sigma, like if someone tells you okay, this process is like 3 sigma, then you know that there's only a 1 in 370 chance that if you randomly sample something from that data set, that it is going to be outside of that 3 sigma range. Or if it is if you consider each of your data sets as one day, then 3 sigma means something that happens yearly, right? So you sometimes hear things like 10,000 year flood or 10-year flood has happened or something like that. This is where that comes from, right? So if given that, say, for example, we have from ice cores, from different forms of different kinds of water data, water table data, we have, say, the last 1,000 years of the Mississippi River Delta data, right? Given then we plot that and we say the data is approximately normal, then we can figure out a major flood is whether a major flood is a yearly event compared to that entire data set, whether it is 1 in every 10 years, whether it is 1 in 1,000 years. So if you hear things like 10,000, like 1,000-year flood or something, then usually this is the kind of analysis that comes from. So once we have these measures, measures of location and measures of spread, next we need to figure out the relationship. These are summary statistics, right? Next we need to figure out the relationship between all your different data points. And to figure out relationships between data sets, we move to another concept which you have probably heard of, is correlation. So correlation and dependencies essentially tell you whether multiple attributes within your data set, how are they related, right? Is if one goes up, does the other go down? If one goes up, does the other not react at all? If both of them go up at this, improve or increase their values at the same time, how strongly do they correlate? So is the correlation are they going up and down throughout the entire data set, or does there come a point where the positive correlation goes into negative? So these are questions that you don't always have to answer when you're doing exploratory data analysis, but you usually end up doing these so that you have some idea of like how the different attributes or dimensions of your data are performing before going into like more detail of how exactly are they performing. This also helps you whether you want to discard any of the attributes. If you have, for example, like your data set has like the data set that I showed you, the SafeGraph data set, it has, I think, around 70-ish attributes. And that is like very difficult to handle. So what I ended up doing is figuring out which of the data sets are like strongly correlated to what I want to find out, and then dropping the rest of it. Oh, sorry, I missed your question, Pedroza. So in real world data set, you'll find that if you work with people, for example, if you work with crowdsourced data, if you work with like collecting data sets about people or about like natural processes, you'll find that a surprising amount of normality in the distributions. Like any kind of, say, for example, you're trying to figure out how much of a like how common a disease is within a group of people, for example. You'll find that very often that it is a normal, it might be skewed by age, by gender, or whatever, but it is very often normal. But if you are not working on a natural data set, say, for example, one of the data sets that I was working with are satellite failure rates in a satellite bus. So satellites that go around the Earth. So that kind of data set where it's a mechanical relationship, a mechanical object that is being hit by multiple things, multiple factors, then you won't find, then very often you will find that those distributions are not normal. Does anyone have any questions? I know someone, or did you just accidentally unmute? Okay. Yeah, okay, yeah, no problem. So yeah, like I said, if you work with like industrial data where some sensor is being affected by like bunch of different things, you'll find that your data is not normal. Another if you work with like communities of people where you're trying to figure out how different communities like work with each other, you'll once again find that communities cluster. Like social networks cluster. So each of the clusters will be normal, but overall the entire process would not be normal. But like I said, always look at your data to figure out whether it's normal or not, because a lot of the statistical like formula and everything like that you might apply to your data, you'll find that they don't work very well on normal data sets, or they don't work very well on non-normal data sets. So you need to keep that in mind. So the way you work with this is an example using R, which I think next Tuesday I'll give you all a brief primer on how R works. R is a data science focused programming language. It's very simple. It's not very different to Python if you have used that. In fact, a lot of Python libraries and R libraries share the same origin. So you'll find it like if you once you get a hang of the syntax, R is very simple and it's very powerful. So yeah, so we try to figure out like correlations and other kind of dependency statistics. An easy way of doing that is try to see if you can fit a model to your data set. Right. You don't need to go into too depth. Like if you don't want to do this, because at the exploratory data analysis part, you don't want to fit like a very complicated model to your data, but a linear model like a very simple linear model would essentially tell you a lot. Like it would help you determine whether that your data set is understandable, whether your data set, like whether the two attributes that you're comparing are related to each other or not. So these things like the very simple positive and negative correlations part. Oh, let me just explain. Positive correlation means both increase at the same time. Negative correlation means like when one increases, the other decreases. When one attribute increases, the other attribute decreases. So yeah, so if you want to figure that out very quickly, fitting a linear model would tell you like whether like a linear model is y equals mx plus c, right? It's a straight line. Well, the straight line would very easily tell you how the data set is performing based on that. You have any? Okay, no questions. Sorry. So another, like once you have this kind of statistical performance done already, like if you have figured out the mean, you have looked at the medians, you have checked out like the standard deviation, you have fit a linear model and it tells you like what the R square value is, like whether it's correlated or not and things like that. Once you have done all of that, then you need to start visualizing it. Remember what I told you about like the gorilla and the data set earlier on in the lecture? So if you're not very careful and you rely completely on this kind of summary statistics, you're going to miss the gorilla. So next, what you do is you start visualizing it. Now, visualizing, for example, the iris data set which are like flower petals or whatever, it might not always be very interesting visualization, but it will tell you like if you plot all the correlations and you plot all the as bar charts or whatever, it will help you understand like what the data set looks like. But the major part why visualization is like visualizing data at the exploratory data analysis step is so important is that like us as humans, we are really good pattern recognition machines, right? Like even the most powerful DALI or whatever AI that OpenAI are developing, they're not as good as us as detecting like patterns within the data. Right. So as soon as you visualize it, as soon as you visualize no matter what kind of data that you're working with, and you put it and you start putting in more and more visualization techniques layering more and more visualization techniques on top of the data, you will be able to spot a lot of like patterns, trends, outliers that is very difficult to figure out like statistically or mathematically. Right. Um, because a lot of times, like the patterns in the data are highly nonlinear. They are like highly complicated to like represent as an equation. You would be able to eventually you'll be able to combine uh, multiple equations together, multiple nonlinearities together to figure out like what's going on in the data. But at the start, you don't want to do that unless you have a good idea of what the data looks like, right? And visualization like essentially tells you like how the data is distributed, how the data is performing. So one of the major things that you need to realize here is that in the real world, data is not just X and Y axis, right? It's not just like two dimensions or two attributes. Most of your common data sets are going to have like 10, 20, 30, hundreds. Like if you're working like with like say, for example, an advertisement company as a data scientist, they're going to give you blobs of data with like hundreds of attributes. So it is not possible for you to visualize all of them. But what you can do is just like make a quick visualization of like, say, for example, the correlation of between all the 100 attributes, so 100 out of 100 by 100, which is like 1,000 figures, and you quickly go like just like lay your eyes on top of them. You will be able to see patterns emerge far more quickly than if you like actually take your time to do like actual correlation analysis, look at the R-square values and things like that. So yeah, you like leverage your strength as a very powerful pattern recognition machine and always visualize your data. Right. So here's a great example. Like this is a very common example of for like all kinds of visualization purposes, right? Like there are thousands upon thousands of data sets, like data points within like the sea surface temperature data set, right? And visualizing, like you can do all kinds of like static analysis on this, but if you want to know like what the data is telling you, you visualize it as you see here, and you can easily tell what the temperate regions of the Earth are, where the Arctic regions are. Uh, like you can guess where the hottest places on Earth are. Like you can see like uh, you can essentially guess also like the northern and southern hemispheres summer and winter are different. So you see this for July 1982, and if you make this map continuously for like different months, you can see the Earth breathe. This red portion, it keeps on moving up like to the up towards the tropics and then move down as it's as during December it's summer for the southern hemisphere and winter for the northern hemisphere. So this band of heat keeps moving up and down the Earth as the Earth rotates. I'll try to give you another example of a project that I work on where the data set is somewhat similar. So this is a project that I worked on. Oh, wait, hang on. Yes. So this is a project that I'm working on with NASA. If you have heard of NASA is launching the Artemis missions, where NASA is going back to the moon. So this is a project where we are trying to like geolocate, help astronauts geolocate themselves on the moon. So you probably know that there are no GPS satellites on the moon for a variety of different complicated reasons that I won't go into here. But because we don't have like like GPS satellites, the only way to figure out where you are on the moon is by dead reckoning. What dead reckoning means is that wherever you land, you know the exact position of your landing spot with respect to the rest of the moon. And then whenever you move, you calculate that as an offset, and that helps you and that's how you keep track of where you are on the moon as you're moving about. Uh, so the problem with that is like small errors build up on each other if you do that, right? So as soon as you land and then you take 2 steps and your dead reckoning is off by like 1 centimeter each time, and as you keep moving further and further away, that error compounds on itself, and it keeps building on itself. So the solution that like I worked on with like some people at the Johnson Space Center at NASA is essentially I suppose many of you have seen how like you can take pictures on from your cell phone of like of an area, and then Google Maps or Apple augmented reality tells you okay where that is. You take a picture of say the New York City skyline or the Houston skyline. I don't know if the Houston skyline is distinct enough for that. And then your app tells you like Google Photos or whatever, Google AR or Apple AR tells you like, okay, you have taken a picture of New York, things like that. So that's what we ended up doing for the moon. Uh, but to do that, to figure out like what the moon looks like, this is the raw data that we were given. This is essentially what's called a digital elevation model of the moon. So this very grayscale imagery, this is the south pole of the moon. We are looking down from above onto the south pole of the moon, and you can see that it's very difficult to see like what's going on in this data set, right? It doesn't look very good. So what we started doing is layering different kinds of visualizations on top of this. like before going into before running our actual process of how we figured out how we geolocated ourselves. And I won't go into too much detail of that, but this is the raw data that we were given. So once we started exploring the data, the first thing we did is we drew contour lines. So each of the lines that you see here are represent like the same altitude on the moon. So that essentially tells us, okay, what are the higher places? What are the lower places? So what are the peaks and valleys? What are the craters? So this big dark circle you see here, that's the Shackleton crater. And that's probably where we'll be, not we, by we, I mean like NASA astronauts would be landing on the moon in like 2026 or whenever Artemis 5 eventually lands. So this is where they would be landing. So this essentially tells us, okay, where the flat regions are, and then wherever the lines are very close together, that tells me, okay, there's a massive slope there. So like the terrain height of the terrain is changing rapidly over there. So once we have done this, then we visualize it using what's called a hillshade map. A hillshade map, okay, this is actually rotated by 180 degrees, so it might be very difficult, kind of difficult for you to understand. So what a hillshade map tells you is that like what are the you essentially uh, create a relief of the map. So what would happen if the sun creates a shadow on the map, and what would it look like? So once again, this is the relief map that we came up with. And as the final step before we started like actually working, this is the map that we created. So this map is like far more understandable. I won't go into too much detail of it, but you can see that this is like far more reasonable to understand like what's going on in the map, where the craters are, where the peaks and valleys are, compared to this image, which is like a random grayscale image. So, so this visualization, which this is like a pre-processed visualization. This is before we start doing any of the like real complicated work on this. So this is where this is how we ended up visualizing our like our working area, our area of interest. And then we started doing our like actual data analysis pipeline where we put in like our all our like actual pre-processing work and our data mining work and things like that. So I hope that was useful. Uh, yeah, just for an example, like you can see, like these are very hard to understand and very hard to see, but this is the kind of data that we were working with. This is the kind of paths that we are creating for the astronauts. So, okay, let's move on to sea surface temperatures. So uh, a major part of visualization, like understanding, like doing good visualization, is proper representation. So what do I mean by representation? Well, representation is mapping the information, mapping the attributes that you have gotten in your that's present in your data set to the visuals, right? Now there's like this is a very complicated work, right? If you there is a course taught by forgot who it's taught by right now, but there are more complicated visualization courses at UH that will tell you like how you exactly do this, like what are the step-by-step processes, how do you visualize like 2D information versus 3D information, how do you visualize flowing, movement information as compared to static information and things like that. I won't go into too much detail here because if you're doing that much work, then it's no longer exploratory data analysis and you've gone into like actual data mining. But you need to figure out like what the relationship is between the attributes that you're trying to visualize, uh, and how do you map that into like different kinds of graphical elements, right? Points, lines, shapes, colors, these are all common graphical attributes, but you need to figure out what which of these do you use when. Like if you're trying to visualize, say, for example, a magnetic field, right? You use like tiny little lines showing like the north and the south poles of the magnet. You don't want to use, I don't know, you don't want to use like just points to show that, right? Because you want to show lines of like magnetic fields. You can't use points to show that. So things like that. So you need to be careful about like what kind of graphical element you use to map your chosen attributes together. Another thing is like you need to combine similar attributes together, right? So if you want to detect outliers, then in a from your attributes, then your data points are very easy to represent as points, right? Points are very easily seen as outliers as compared to more complicated shapes or lines or whatever, right? If you draw everything as continuous contour lines, very difficult to figure out like where the outliers are as compared to discrete points, etc. So here's a very simple example of like how uh, like uh, university evaluations are distributed. Right? So uh, it's very easy for you to look at look at this like random image and tell like okay, which universities are like located where as compared to uh, with in relation to each other, right? So now let's go to like the very common visualization techniques that you'll be using for like your task 1 and task 2 or whatever. These are the visualization techniques that you've all used, you've all seen in school, you've all seen in university. So the most common of them are like histograms. Histograms are very easy to, you all know what histograms are. You distribute the value, you take a single attribute or a single dimension or a single variable, then essentially you divide the value into bins, and then you plot each of the bins showing how many of your data points fall into each bin. Uh, your histogram would change dramatically depending on how many bins you have chosen. So if you choose, say for example, you choose just one bin, like only 1 point can fall into a bin, then you have not drawn a histogram. You have essentially just plotted them as a line plot. But as soon as you start combining multiple values together, you start seeing patterns start to emerge, right? So that this petal width data set is a left skewed data set, as you can see. So there's a massive peak on the left, and there are multiple smaller peaks that you may or may not consider as peaks. So you can just consider this as one peak with a massive skew on the left. Okay, so if you have any questions, let me know. Yeah. Oh, I missed your comments. Yeah, thank you. I'm very proud of that NASA project. It's going well. Uh, so here's another way of combining histograms, because you know histograms are a single attribute or a single variable working together, right? So you can combine them together and create a 3D plot of showing a 3D histogram, like a joint distribution between different histograms. Um, I will let you know this though, that in general, 3D plots like this, not always very helpful. They're not easily understandable for one. And this can also be seen in like other ways, right? Instead of using a joint histogram distribution, if you just plotted them as X, Y, as a line plot with each other, you'd probably be able to see the same thing. Apologize for the what sounded like thunder. So yeah, so I'll always advise you, don't rely over much on 3D plots, right? Focus on focus on creating, because 3D plots, when they're interactive to the end user, to you, they're good. But when you are doing exploratory data analysis, you don't really need the kind of interactions that you need here. So I would always recommend going for very simple 2D plots over complicated 3D plots. Right. Okay, so histograms. Like I said, choosing proper bin sizes is very important, because on average, you can create equibins, right, where points are equally distributed within the bins. But always remember, if you do that, you are very likely to miss outliers or peaks, or more importantly, if you create like equal bins, you're very likely to miss troughs. Like you're very likely to miss minimas, which can create problems, because you don't always know, because if you don't always know where the minimas of your data set are, uh, then you don't know where the weaknesses of whatever you're trying to model are, right? So equal binning is good as a first step, as a first pass, but in general, don't rely over much on equal binning. Uh, so uh, explode the data set first, and then then reconstruct your bins so that you're more easily able to like bring out whatever stands out in the data set to you. And I'll let you know that questions on histograms are almost certainly going to be on your midterms. And it'll be a very simple question. Like you can't really go wrong in the question, but you need to understand like what histograms, like why you are binning, like what attributes, like what does it mean for you to equally bin something? What does it mean for you to change the size of your bin and things like that, right? So yeah, it won't be a very difficult question. Don't worry. Like these are going to be very like obvious answers, but you need to, once again, you need to understand what histograms need, like what you're trying to show in a histogram, essentially. So yeah, I talked about box plots before. Box plots are a far more useful like interaction point between visualization for all kinds of attributes. Much better compared to, like, in my opinion, much better compared to histograms. Um, so, okay, we don't use this particular variation of a box plot because we don't really stretch to the 90th percentile, right? Like that is like way too much. We usually stretch to the 75th percentile, right? So what we mean by this is that where you see this where you see this the whisker, the whiskers of the box, they should usually stretch till the 75th percentile rather than the 90th percentile, because that's where a lot of your essential data falls. So uh, when next week when I talk about, when I use R, I'll talk more in more detail of like how to create this kind of box plot in R. And then next week we will also tell you how to do this in Python if you're more comfortable with Python. But box plot is like essentially any kind of data analytics platform will let you use box plots. And you don't really need to do a lot with them. They're just there for quick visualizations. Okay, a series, like you don't really look at an individual box plot in isolation. You look at, if you have like 10 attributes, you look at 10 box plots, like all side by side, and then you take a guess, like you automatically have a good idea of like, okay, well, how those attributes are being distributed as with respect to something else. Um, so this is how like you create a box plot in R. I won't go into too much detail for this actually, because you're gonna learn this in much more detail. This comes up as a midterm question fairly often. So you're going to you can look at the slide in this year 33, 37 website, and you can look at what's going on there, but I'll go into more detail next week. This will probably be, once again, a midterm question for you. Like, create a box plot given a particular data set. So all you need to know is how to calculate your median. You need to know how to calculate the interquartile range, which is essentially the size of the box that you see here, and then how to find out how to position your whiskers and how to plot your outliers. So you'll need to look into that. It shouldn't be too difficult. Oh, okay, it's 12:41. So I think I'll wrap up here. So like I said, I saw that a couple of you have already sent me emails with about the September 9th uh, Phillips 61 thing. So let me see if I can go back quickly to the first slide. Yeah, so it's on 535 Portwell, September 9th. So that's next Friday. Starts at 7:30 a.m. in the morning, and it will kick off at 8 a.m. So it's a good recruitment opportunity, and UH has been doing a lot of work with the Houston Food Bank people. So turn up. It might be useful to you. Next week, we will also be giving you the task 1 data sets. If you want a hint, you're going to be working on a marriage and divorce data set. If that's a hint for you, and you'll be given details of the data set and all that on Labor Day and other details. Oh, okay, good question. So box plots. See, box plots don't really tell you trends in the data. It tells you how the data is distributed, where the outliers are, and where you should concentrate on the data, right? So if your data set, if you're, say, for example, let me go back to the thing. And the data look like here. So if your box plot looks something like this, then you know that like a lot of your data is concentrated in the center. That is useful. But if the box in the box plot is like stretched like taffy, then you know that like you can't really sample the data set centrally. Right. And it might also mean that your data set is not normal. There might be multiple peaks in the data set. It might be spread pretty badly. If your data once if this box is like towards it's small, but it's towards one of the ends, then you know that your data set is skewed, whether it's left skewed or right skewed, things like that. For trend analysis, you generally don't really need to do box plots. You do correlations or you do line plots. You fit a linear model to your data set and then you see what's going on there. Yeah. So I hope that answers your question. You don't really use box plots for like that kind of trend analysis. You use it for understanding like the distribution of the data set more than trends in the data set. So yeah, I think I'll wrap up here. It's like, yeah, like I said, it's Labor Day and I want to let you guys off quickly. And also I have a paper submission, so yeah, I'll be busy as well. So if you have any questions, feel free to ask us as the TAs, and yeah, send me the email for the Phillips 66, Phillips 61, 66, 69, I forget, for the Phillips event. And yeah, that's it. And okay, I will tune out here, everyone. Have a good rest of the week and send me any questions that you have. Take care. Bye-bye.
Thank you.
Thank you.